Welcome to the next lecture in the course Thermodynamics and Fluid Mechanics. This lecture series is part of Basic Mechanical Engineering, and in the first lecture we have gone through what are the basics of thermodynamics. We saw what is a state function, path function, process function. Then we saw different types of energies, internal energy, work, heat. We also saw different types of processes. We will try to have little more understanding of this subject. So, this is on thermodynamics, equilibrium, process and thermometry. Content. What are the different types of thermal equilibrium? We will try to see reversible and irreversible processes, different thermodynamic processes and graphical representation, cyclic processes, zeroth law of thermodynamics. We saw what is zeroth law in the previous lecture, very basic. Then we will try to see measurement of temperature. Then we will try to move into the topic of thermometry, properties, definition and application. And finally, common temperature scales and their interconversions, because we have Kelvin, we have Fahrenheit, we have Celsius. So, there are three different things. By the way, when we try to measure human body temperature, we always say 104 degree. It is 104 degree Fahrenheit, right? And when we try to talk about room temperature, we try to talk about degree Celsius. And when we talk about sub-zero, we always talk in terms of Kelvin. So, various applications are there. You should know the conversion scales. Types of thermodynamic equilibrium. A system is said to exist in the state of thermodynamic equilibrium when no change in any macroscopic property is registered. Macroscopic property is registered if the system is isolated from its surrounding. So, what we are trying to say is, you have a system and it is isolated. Isolation is basically you put thermocol around it, that is it. A system is said to exist in state of thermodynamic equilibrium when no change in any macroscopic property, pressure, volume, temperature, if the system is isolated from the surrounding. If you seal it, nothing is going to happen. An isolated system always reaches in course of time a state of thermodynamic equilibrium and never depart from it spontaneously. It slowly moves out of its existing state. So, that is what happens in your thermoflask also, right. An isolated system always reaches in course of time a state of thermodynamic equilibrium and never depart from it spontaneously. Therefore, there is no spontaneous change in macroscopic property if the system exists in equilibrium. This is very important. If the system exists in equilibrium, there is nothing called change in macroscopic property. For example, you take a pan which is there in the normal kitchen condition where temperature, pressure, everything is set like room temperature. Then you keep a pan, and this pan you are trying to, without heating it, you are just keeping it on place. So, therefore, there can be no spontaneous change in the macroscopic property if the system exists in equilibrium condition. Moment you heat it from the bottom or moment you try to load it from the top by a pressure, then you can see there is a change. So, thermodynamic studies mainly the properties of physical system that are found in equilibrium state. Please try to underline this, because you have to always understand what we talk will always be in equilibrium state. So, if there is a sudden change and all, we do not look into it for our discussion. A system will be in a state of thermodynamic equilibrium if the conditions for the following three equilibrium satisfies. One is mechanical equilibrium, equality of pressure. When we say chemical equilibrium, equality of chemical reaction rate. Thermal equilibrium, equality of temperature. So, all these things are equilibrium states. In the absence of any unbalance of these forces within the system itself and also between the system and the surrounding, the system is said to be in state of mechanical equilibrium. If the unbalanced force exists, either the system alone or both the system and the surrounding will undergo a change of state till mechanical equilibrium is attained. So, you pull a string, you leave it, it keeps on jumping till it comes to the normal state. So, if there is no chemical reaction or transfer of matter from one part of the system to another, such as diffusion or solution, the system is said to exist in the state of chemical equilibrium. See, diffusion is something very interesting phenomena which is exhaustively used in material science. So, here what happens, there is a porous structure or there is a solid wherein which you pressurize and push the atoms inside. You have a sponge where water gets diffused inside, right? All the pores are getting filled with water, it sucks. So, if there is no chemical reaction or transfer of matter from one part of the system to another, such as diffusion or solution, then the system is said to exist in chemical equilibrium. When we talk about mechanical equilibrium, it is the same. If an unbalanced force exists, either the system alone or both the system and the surrounding will undergo a change of state till mechanical equilibrium is attained. When the system exists in mechanical and chemical equilibrium, is separated from its surrounding by a diathermic wall, a wall which allows heat to flow. And if there is no spontaneous change in any property of the system is said to be in thermal equilibrium. When this is not satisfied, the system undergoes a change of state till the thermal equilibrium is restored. So, what I am trying to tell you is mechanical equilibrium, chemical equilibrium and thermal equilibrium, when will it be achieved and how it will be achieved. So, that is what we are saying. And why is this important? Because later when we look into several of these cycles, we will be using these properties. So, we discussed about state till mechanical equilibrium is attained, chemical equilibrium when it will be attained and thermal equilibrium when it will be attained. And this is pretty interesting, diathermic wall which allows heat to flow. For example, you can try to have a cloth as a wall, a cloth as a barrier as a wall. So, wherein which heat tries to move out. For example, when we make sweets, many of the sweets what we do is we try to pour the sweet on top of a wet cloth and allow this sweet to from a hot condition to get into a cold condition, and wherein which the cloth whatever we use behaves like a diathermic wall, allows only the heat to flow through, right. So, when the condition of any one of the three types of equilibrium are not satisfied, then it is called as non-equilibrium state. You have to understand equilibrium state, right. So, that is what we said. Therefore, there can be no spontaneous change in macroscopic property if the system exists in equilibrium state. The thermodynamic studies mainly the properties of physical system that are found in equilibrium state. And here we have defined all the three equilibrium: mechanical equilibrium, chemical equilibrium and thermal equilibrium. So, chemical equilibrium is, suppose you try to keep a matter which is there in an open atmosphere. So, if there is no chemical reaction or transfer of matter from one part of the system to the other, such as diffusion or solution, then it is said to be in equilibrium. For example, you keep a glass jar in a kitchen. I always give you examples of kitchen because you can correlate it very fast. So, there what happens, it is in a neutral state. So, that is called as chemical equilibrium. So, when you try to talk about a system, when the conditions of any one of the three equilibrium are not satisfied, then the system is said to be non-equilibrium state. And throughout we only talk about equilibrium state. So, now let us look into reversible process and irreversible process. Elastic limit, a same analogy in design. So, wherein which we have an elastic rubber band, we put a load, we release it, it comes back to its same state. So, that is called as reversible process. So, in the same way in thermal also we have reversible process and irreversible process. So, what is reversible process? Before getting into the definition and other part, we will try to understand the graph. So, you have y parameter, x parameter. This y can be temperature and x can be taken as time. You can also try to have pressure, you can try to have volume, whatever it is you can try to have, and here you can try to have mass, etc., etc., etc. You can take y any value, x, any value, or any magnitude, whatever. Value means you can try to take temperature, pressure, you can try to take even voltage, by the way, you can try to take volume also. And please keep in mind, friends, that when you try to plot x, y, it is always a good idea to also plot the units. So, millimeter cube, pressure in terms of MPa, temperature in terms of degree Celsius, time in terms of seconds or hours, whatever it is, mass in terms of kgs. So, it is good idea to write the label the axis with the units. So, if you see reversible, so A, when you want to go from A to B, it follows a path, right. So, and then if we wanted to reverse it in the same path, it is called as reversible process. If it tries to take another path, it is called as irreversible process. Okay. A process in which the system and the surrounding can be rebuilt from the final state to the original state without any change in thermodynamic property of the universe. It is called as reversible process. When you can try to, in which a system and the surrounding can be rebuilt from the final to the initial or the origin state without any change in thermodynamic property, it is called as reversible. Now, let us try to understand the graph. Let us assume that a system has experienced a modification from a state A to state B, and there is no change in the universe. The process is expressed as reversible process if the system can restore from B to A. Reversible process can be completely reversed and there is no trace left to demonstrate the system has experienced a thermodynamic change. So, thermodynamic change, pressure change, volume change, temperature change, nothing is there. From A it goes to B, from B it goes to A. For the system to sustain the reversible change, it must have infinitely sluggish, but generally it is always irreversible. All the state fluctuations that occur during reversible process, A to B, B to A, are in thermodynamic equilibrium with each other. So, there are two consequent contingencies to doing the reversible process. Basically, the process must take place in an infinitely short path, and second, all the original and the final state of the system must be in equilibrium with each other. So, this is very important. Basically, the process must take place in an infinitely small path. Okay. So, very small path you will try to do. However, if the heat content of the system remains constant during reversible process, it can be an adiabatic process. This process is also called as isotropic process, that is, the entropy of the system remains constant. So, you should understand this point. In a reversible system, the entropy of the system remains constant. Okay. If the heat content of the system remains constant, heat content is always constant, which is very difficult in reality, remains constant during a reversible process. It can be adiabatic process. This process is also called as isotropic process. So, entropy, when the temperature is, when you take is constant, right, heat is constant because there is no difference in temperature, heat is constant, then it is the entropy of the system also remains constant. What are the conditions for reversible process? There should be some condition. There are two main conditions. There are many, but the most significant conditions are two. The process should occur in infinitesimally small time, the process reversible. Secondly, all the initial and the final state should be in equilibrium with each other. So, pressure, temperature, volume, pressure, temperature, volume, in case you have a system of a three-dimensional axis presentation, then the initial and the final state should be in the equilibrium with each other. The reversibility in thermodynamics, the phenomena of undergoing reversible change is also called as reversibility, ability to reverse, that is reversibility. In actual practice, the reversible process never occurs, but for simplification in calculation, we always try to take it as a reversible process. We try to do, in the problems you will see, they would have written in the question itself, it is a reversible process. So, the understanding what I am trying to impress you is, please assume that the other conditions are constant. There is no heat loss, right? That's what it is. So, the reversible process never occurs. Thus, it is an ideal or a hypothetical process, reversible process. When we try to write a question, we say in a reversible process system, for example, in a refrigerator from point A to point B, whatever it is we write. So, that means to say it is idealistic case. So, example, although no actual change is completely reversible, but the process of liquefaction and evaporation, solid to liquid liquefaction. So, for example, ghee or butter to ghee liquefaction, then evaporation of a system performed slowly are practically reversible. Similarly, slow compression of a gas in a cylinder is a reversible process. Slowly you have to compress, as gas can be expanded slowly by decreasing the weight of the piston to reverse the operation. So, you can try, but these are all idealistic case. Types of reversible process. So, here we saw reversibility, ability to reverse. Then we saw an example. Then types of reversible process. So, there are two types of reversible process. One is internally reversible process. Another one is externally reversible process. Internally reversible process is a process is clarified to be internally reversible if no irreversibility occurs within the system's termination. No reversibility occurs within the system's termination. In this process, a system passes through a series of equilibrium state, and when the process is reversed, the system passes through similar equilibrium state, replacing its original state. So, you move from here to here, then you move back from A to B, then it is moving back to A, B, right, B to A. So, if the process, a system passes through a series of equilibrium state, and when the process is reversed, the system passes through similar equilibrium states, replacing its original state. What are external reversible process? In an external reversible process, no reversibility occurs outside the boundaries of the system during the process. Internal means within the system's termination, right? Within the system, this is a system, right? This is a surrounding. So, within the system, it is internal. Then outside the boundaries of the system during the process is external reversible process. For example, if the surface of contact between a system and the force is at the same temperature, the heat transfer between the force and the system is also an external reversible process. Okay, internal reversible, external reversible. Now, let us get into irreversible process. In reality, all the processes are irreversible. Irreversible process are correspondingly called as innate process, because all the actions that take place in nature are irreversible process. The natural process is due to the finite gradient between the two states of the systems. For example, the temperature gradient between two bodies causes heat to flow. Higher temperature HT, lower temperature, there is a gradient, right? Transfer, there is a gradient. It can be attached to each other, it can be away. Between two bodies causes heat to flow between the two bodies. This is actually the natural flow of heat. Also, when water flows from a higher level to a lower level, current overflows from higher potential to a lower potential, etc. The original state of the system and the environmental condition cannot be recreated from the final state in an irreversible process. So, friends, I am making it very clear. In reality, whatever is the process, it is called as irreversible process. But for understanding, for subject, for simplification of mathematically solving, we always assume reversible process. And reversible process is valid when the change are infinitesimally very, very small. Okay. The colored state of a system are not in equilibrium with each other on the path of modification from the original state to the final state during irreversible process. So, in an irreversible process, the entropy of the system increases significantly. This point is very, very important, because in reversible, we try to say reversible, the entropy of the system remains constant. But in irreversible process, we try to say that it is entropy keeps changing, increase significantly, and cannot be downgraded back into its most critical value. Like in reversible, here also we have internal irreversibility and external irreversibility. The ability to reverse is reversibility. In this internal irreversibility, the disruptive effect is present within the working fluid. Convection, right? So, external irreversibility, the dissipators subsits outside the movable working fluid. For example, you have a hot body, a fluid is flowing on top of it, so that the temperature of the body can be reduced. Where do we use? In metal forming, it always happens. After hot working is over, then you have the billet, which is in a red hot condition, right? So, now what do we do is the external irreversibility, the dissipators subsits outside the movable working fluid. Example, mechanical friction due to external forces. So, these are external irreversibility. Some important points about irreversible processes. In the irreversible processes, the initial stage of the system and the surrounding cannot be restored from its final stage. That is first understanding. During irreversible process of various states of the system, of the path of the change from the initial to the final are not in equilibrium. This is very important, are not in equilibrium. During irreversible process, entropy increases. The phenomena of system undergoing irreversible process is called as irreversibility. So, irreversibility process examples: the conduction of heat from hot body to a cold body is an irreversible solution. A friction which is production of heat by the friction when two metal bodies rub against each other, or when you try to rub your hand, two bodies when you try to rub each other, there is a friction. This friction leads to heat. Producing a heat by passing of current through an electrical resistance. So, you try to have a cable, or you try to have a wire, and then you try to keep this wire which between positive and negative. When the current flow is very high, this goes to red hot condition. So, producing heat by passing of current through an electrical resistance, or the bulb, the incandescent bulb, you pass and then that tries to emit light. Transfer of heat by radiation, right? That is also irreversible. An explosion, irreversible. Inelastic deformation, then magnetization or polarization with a hysteresis, then spontaneous chemical reaction, then we have spontaneous mixing of matter of various states. An explosion and spontaneous chemical reaction are the same. For example, you try to drop sugar in a liquid, it tries to dissolve. So, spontaneous chemical reaction can happen, and then spontaneous mixing of matter of various states is also there. These are some of the examples of irreversible process. Now, it is very clear, in reality irreversible process only exist. So, now let us try to distinguish the reversible and irreversible processes. Takes place in an infinite number of infinitesimally small steps, would take infinite time to occur, reversible process. Here it takes place in a single step, irreversible process. It is imaginary, it is real. It assumes the presence of frictionless and weightless piston. It takes everything in reality actual. The problems you will try to understand this, because when we try to do a problem on compressor, we will try to say it follows a reversible process. So, then you should understand there is no friction, there is no weightless and a weightless piston, right. The system is in equilibrium at all state of its operation. Here the system is in equilibrium only at the initial and the final state in irreversible. All changes are reversible when the process is carried out in the reversible direction. Here all after the process changes do not return to the initial stage by themselves. Extremely slow. This is proceeds in a measurable speed in reality. Work done is reversible. work done in an irreversible expansion. Process is smaller than the reversible one, is greater than the corresponding irreversible process. So now it is very clear. Till now whatever we have deliberated, you know now clearly reversible, irreversible. Reversible, what are the conditions? Irreversible, what are the conditions? Now let us try to look into thermodynamic process. A thermodynamic process involves a transfer of energy within a system or between systems. Transfer of energy, this can be heat, it can be mechanical, whatever it is. So, involves the transfer of energy within a system or between two systems, within one system or the other system. It involves properties like pressure, temperature, volume, P, V, T. These are the normal things, and we also have entropy which comes. So, we will later see, we will draw a PV diagram, we will draw a TS diagram. Okay. The present value of the property of a system are called as a thermodynamic state of the system. Thermodynamic state of the system is the present value of the properties, right. An example of thermodynamic process is food staying cold inside a refrigerator. If you switch off, it becomes to normal. But when there is an energy which is applied and that energy is trying to throw a cold air inside a refrigerator, the food whatever you keep and the food temperature and the outside temperature, almost it is in equilibrium. That is what they say. An example of thermodynamic process is a food staying inside a refrigerator. In a refrigerator, the heat is pulled out of the thinner compartment and transferred to the outside air. So, what happens? How does the heat gets extracted? In a refrigerator, the heat is pulled out, because when you keep a hot milk inside the refrigerator, the hot milk temperature has to be pulled out, right? The heat is pulled out of the inner compartment and transferred to the outside air. That is what it also happens in the refrigerator, also in the AC. Okay. So, the heat is extracted and of the inner compartment and transferred to the outside area. You can also use AC as a heater. So, when we use the AC as a heater, so now what happens? It tries to throw the cold air inside the room outside and give you hot air. So, you have dual modes today available. In refrigerator, it is only hot to cold, but here in AC, you can have hot to cold, cold to hot. So, these are the different types of process. We already had a small introduction. So, isochronic process, isobaric process, isothermal process, adiabatic process. What is isochronic process? Volume is constant, delta V is 0. So, the constraints will be the piston is not allowed to move, is isochronic. So, here whatever happens, then the heat is applied, whatever it is, the piston is locked. The piston is locked. So, whatever happens has to happen, the temperature has to go out, pressure has to go out, but maintain a constant volume. When we talk about isobaric, P is constant. So, there is no change in P pressure. So, what happens is the piston is allowed to move up and down freely. As and when you try to heat, okay, heat, what happens? This tries to expand, right, expand. So, moment there is an expansion, so the pressure is nothing but force applied per unit area. So, now the area in turn we can connect it with volume, the volume gets expanded. So, the pressure remains constant, right. So, isobaric, P constant, delta P is also constant. When we talk about temperature, it is isothermal process, delta T is equal to 0. So, when delta T is equal to 0, the temperature of the system is constant, the volume can expand, the pressure can expand, but the temperature is always constant. When we talk about adiabatic, neither entry nor leaving of the system of Q, neither entry or nor leave the system is there. So, you will have adiabatic means Q, whatever is there, it will neither enter nor leave the system, the Q is maintained. So, that is adiabatic process. Friends, I understand, or I also request you to see what is Q. So, you go back to the previous lecture and you will see what is Q. Okay. So, these are the 4 different types of processes which are there in thermodynamics. As isobaric pressure is one in which the pressure remains constant throughout the process, the key characteristics as volume and temperature may change. Common in systems with movable boundaries like pistons. If you go back, isobaric, piston can move up and down, and here also we assume that there is no friction between the piston and the walls. Example, boiling water in an open container at atmospheric pressure is a isobaric process, because the atmospheric temperature is constant. Heating air in a piston cylinder assembly with a freely moving piston. When you try to inflate, or when you try to push air into a tube, then steam generation in boiler operating at constant pressure. Why are we operating at constant pressure? Because what happens is the materials put always a restriction on top on the increasing pressure. So up to a certain level, they try to have a very good material, and then this material can withstand up to a certain pressure. So now what we do is we try to control the process by maintaining at a constant pressure. So that's what steam generation in boilers operating at a constant pressure. Now let us look at isothermic process or isothermal process, which is nothing but a constant temperature. Okay. So an isothermal process is one in which the temperature remains constant throughout the process. So here internal energy remains unchanged in an ideal gas. It requires slow process with efficient heat exchange to maintain constant temperature. Okay, the heat has to be dissipated, and when the heat has to be dissipated, you cannot do it instantly. It requires a slow process with efficient heat exchange to maintain a constant temperature throughout the process. So here internal energy does not change. So if you go back to the figure, isothermal process, you can see here again there is a wall. So in this you have a boundary, around the boundary you have a diathermal wall. So this diathermal wall means these walls are, I gave an example of a cloth. You can also have a sponge, right? You can also have a sponge, you can have a cloth. So there is a transfer of heat happening, which is there. The common, so requires slow process with efficient heat exchange to maintain constant temperature. Melting of ice at 0 degrees under atmospheric pressure falls in the example of isothermal process. Melting of ice at 0 degrees Celsius under atmosphere, 0 degrees Celsius, right? Very slow it can happen. Slow expansion or compression of gas in a thermostat controlled environment. Slow expansion or compression of a gas, which is used in AC cooling. Evaporation of water at its boiling point under a constant pressure. All these things are isothermal process. It is pretty interesting. Evaporation of water at a boiling point, 100 degrees Celsius, under a constant pressure. So you have a piston, you put a weight on the piston, you keep on be heating. So you see pressure is constant, and volume you will try to play, then you try to get whatever it is. So isothermal process. Then isochronic process is constant volume. And isochronic process is one in which the volume remains constant throughout. So volume remains constant throughout. So you put a stopper and you have the volume remains constant. So no volume. Since the work done does not change, any heat added or removed changes the internal energy and the pressure. Any heat you add or remove changes the internal energy and pressure. Heating of a gas in a sealed rigid container. So you put like an isolated system, right? Heating of a gas in a sealed, right? Then combustion of fuel in an engine cylinder before the piston moves is also constant volume. When you go to IC engines, we will see that basics of IC engine, we will see constant volume process. The pressure increases in a pressure cooker before the safety valve operates is a constant volume process, because the pressure cooker volume is constant, right? So before it could push the safety valve, it is considered. So now friends, you will be able to distinguish isobaric, isochronic, isothermal. Then let us see the last one, which is adiabatic process. What is so in the three? What did we see? P constant, V constant, T constant. Now what is pending is S constant, right? That is entropy. Adiabatic process. In adiabatic process is one in which no heat is transferred to or from the system. No heat is transferred from one energy to the other or up to down, whatever. No heat is transferred to or from the system. We have a constant entropy here. The temperature changes due to internal energy variation. It occurs in an insulated system or during rapid process where the heat exchange is negligible. So, rapid compression of air in a bicycle pump is a adiabatic process. Rapid compression of air. Why? An adiabatic process is one in which no heat is transferred to or from the system. So, here rapid compression of the air in a bicycle pump. Sudden expansion of gas when the pressurized container is open. When you open, for example, Pepsi bottle, sudden expansion of gas when a pressurized container is opened. The expansion of gas in turbine where insulation minimizes heat exchange. So, these three are there. So, majority of the time we will try to give which process the system follows, so that it becomes easy for you to use the equation. So, it can be isobaric, isochronic, isothermal or adiabatic. Adiabatic, friends, keep in mind entropy. So, what is entropy? We have seen in the previous lecture. So, now polytropic process. Polytropic is a thermodynamic process that obeys the relationship PVX equal to a constant. So, P is pressure, V is volume, X is polytropic index. PVX equal to a constant. C is a constant. So, now what is the value of X is the question. So, the polytropic index will take a value between 0 to infinite depending upon the process. So, now let us see what do we do in which process. If X equal to 0, it is called as isobaric process. P, V, X equal to a constant. When X equal to 0, P becomes 0. So, there is isobaric process dP is equal to 0. When we take X equal to 1, then it is PV equal to a constant. So, then it is called as isothermal process. When X equal to N, then it is called as polytropic process. If X equal to gamma, then it is called as adiabatic process, where dQ entropy is 0. When X equal to infinite, then it is isochronic process. dV is equal to 0. So, friends, keep this in mind. The basic formula is PV X equal to a constant. Now, depending upon isobaric or isothermal or isochronic, adiabatic, you change the value of X. Okay. Graphical representation of expansion, compression, expansion. Okay. So, the change in pressure with respect to volume, change in pressure, I told you, Y and X, change in pressure to volume is represented in this graph. So, that means to say this, let us take it as P1, right, and let us take it as P2, let us take it as V1 and let us take it as V2. V1, V2 is V initial, my V final. So, then this becomes initial, then you try to take it as pressure final, whatever it is, right. So, you try to take it. So, now let us try to understand the process of expansion graphically. The change in pressure with respect to volume are given in a PV diagram. So, whenever we try to call it as a PV diagram, it is pressure versus volume. The efficiency of a system can be determined using the PV diagram. The area under the curve of a PV diagram gives the work done to or by the system. Please understand this point. The area under the curve of PV diagram gives the work done or by the system. For a PV diagram of expansion, it is clear that that for same volume of expansion, the area under the isotherm curve is more than the adiabatic curve. So now what is expansion? So when in the PV diagram, when the expansion happens at a given pressure, so then the volume goes to the final state, right? From a PV diagram of expansion, this is expansion, it is clear that for the same volume of expansion, the area under the isothermal curve is more than the adiabatic curve. So this is what it is. So you see the slope of isothermal is higher as compared to that of adiabatic. Therefore, isothermal work is more than adiabatic process. So what we are trying to say is, we are trying to say this is the area. So let's draw it like this, right? This is one, this is something like this. So this is the area we are talking about. So this is the area under the curve, Therefore, the isothermal work is more than the adiabatic work, because you see the area which is there is under the curve is very low. When expansion happens, the volume changes. When expansion happens, volume changes. So V1 to V2. So the pressure will fall from P1 to P2, whatever. Therefore, the isothermal work is more than the adiabatic. For the compression curve, so this is expansion. Expansion means moving, right? So you can see isobaric, pressure constant. Then what happens to the volume? Changes. Yeah, then x equal to n is polytropic. This is for expansion. What happens when you do reverse of it? Compression means from Vf, it is going to, from Vf it goes to V1, Vf to V initial, right? It is compression. So now for the compression curve, you can see everything goes from Vf, or this I have put it as Vi. So if you compare with the previous graph, it is Vf, Vi. So you are trying to compress from here volume to reduce the volume. Okay. From the compression curve, it may be seen the area under the adiabatic does more work than isothermal. So you see here, it is for compression. This is for isothermal, this is for that, right? So during expansion, isothermal does more energy, more work, and during compression, the adiabatic curve does more work. It can be seen that the area under the adiabatic curve is more than the isothermal curve. In the case of compression, the work done is calculated by adding a negative sign, because it is compression. So compression is negative sign. Please keep that in mind, right? Therefore, even in compression, isothermal work will be more than the adiabatic work. Therefore, even in a compression, the isothermal work will be more than the adiabatic work.
Thank you very much.